Hey everyone, welcome back to this class. In this video, I just want to go over the results for the final exam. Some of you have requested that we walk through this, so I'll go ahead and make a video for it. So here I've got the version 1 opened up, and we'll take a look at this first question. So version 1, part 1, we're looking at this DC residential power distribution circuit. So how many unknown node voltages are there? We know this bottom left is ground, so that's 0. We know this middle left is V2 because we're going through that constant voltage source. And then this top left is V2 plus V1. Right, we're going up 2 voltage sources there. And that leaves the top right to be an unknown. We'll call that A. This middle right to be unknown, we'll call that B. Bottom right, C. So we have 3 unknown nodes. I've gone ahead and labeled them. And for part B, we are going to label the current directions. So I've got I1, I2, I3, and I'm just going to label them all going down to the right and then recombining through R6 to get back to ground. And it doesn't matter how you do this as long as you write the equations appropriately. So if I do a KCL at node A, I've got I1 coming in, I2 and I4 going out. So those will all add up to be 0. And if I expand out I1, so right, I'm starting, I1 is going from left to right here. And on the left, we have V2 plus V1. And then on the right, we've got VA going through R1. And for I2, we're going from VA to VB. So I've got VA minus VB divided by R2. And then in a similar fashion, I4 is VA minus VC divided by R4, and that will sum to 0. So then you can have similar fashion to find KCL equations at node B and node C. I'll just write the currents, and then you'd have to, expand them out accordingly. So at node B, you've got I2 and I3 going in, I5 coming out. And at node C, we've got I4 and I5 going in, and I6 going out. So I think most people got that correct. Where shit started to hit the fan is part C here. It says, what can be said about voltage across R5 with respect to R4? So in this version, right, we're looking at R5 and R4, and there's a parallel path here through R2. So clearly the voltage across R5 must be less than R4. VR5 is less than VR4. Hopefully that makes sense, right? Because the voltage in parallel is the same, right? So any path from A to C. So I've got one path this way, got one path this way from A to C. So those are the same, which means that there's another voltage through R2 that you have to get through to get the same voltage across R4, taking that path. And for part D, we are putting in a voltmeter to measure the bottom right node voltage. And so that's going to be node C here. And when we're measuring a node voltage, that's always with respect to ground. I'm going to take the positive reference to node C, the negative to ground there. All right, so now we can take a look at version 2 real quick. So A and B, these are the same. We can look at part C. That's more important here. So R2 versus R4, and it's the same idea. R2 and R4, well, there's a path through R5 that would be in parallel. So clearly the voltage across R2 must be less than the voltage across R4 there. And for part D, I'm drawing in a voltmeter to measure the voltage across R4. And this is where, things were a little tricky maybe for some of you. But the idea is we take the positive reference and the negative reference of our voltmeter, and we put that in parallel with R4. Right? We're no longer measuring with respect to ground. Some people would put it like that, and that's not the voltage across R4. We're looking at just a single element, just this R4. Hopefully that makes sense. So that's for version 2, and then for version 3, right, so these have been done. Part C, what can be said about the voltage across R2 with respect to the voltage drop across R5? So we're looking at here and here, and quite frankly, there's nothing that we can really say without knowing specific values. Hopefully that makes a little bit of sense. We can't really make any judgment calls like, sure, we've got VR2, from here to here, or V2 from there to there, V1 plus V2 from there to there. But we can't really say anything about the drops across these specific elements. So nothing can be said, unfortunately. Might have been tricky for some people, or like you could have said, it depends. And for part D, similar thing where you're drawing in a voltmeter to measure across R5, right? And it's no longer just a node voltage. We're going here, and that will give you the voltage across R5. So hopefully that makes sense. Moving on to number 2 and back to version 1. So we're coming up with an equation that describes the unknown node voltage there. One way we could do this is just 2 resistors, so we can find that. Well, first off, this is ground, so that's definitely 0 volts. This is a constant voltage source, so up here we definitely have whatever Vin is. So the only unknown node voltage is top right. We'll call that V out. And we're looking for an equation to describe that. Well, V out is most certainly whatever the current is, because we're all connected in series here. So the current times RL. And so what is that current? That current, well, we're applying V in divided by R plus RL, right? We're applying V in across this path of elements in series. We find that equivalent resistance there. We divide by V in, and that gives us the current, which then gives us that V out is V in times this ratio of RL divided by R plus RL. And that goes back to that whole voltage divider principle, right? So we're looking at the ratio of this guy with respect to this entire network. So hopefully that is pretty easy for you guys. And we're looking at what happens to V out considering RL. So as RL goes up, V out approaches V in as RL goes up. Right, so as this RL term starts to dominate both the numerator and the denominator, then we're going to have a ratio of 1 to 1. So at some point V in, or the V out, the output voltage becomes V in. If we were to sketch that, we've got RL increasing there, and we're looking at V out, and at some point it approaches V in, at which point it's going to start asymptotically approaching it. It's going to make very little difference how much it goes up. But it'll never quite get there, right? We still have this R term in the denominator, unless R was 0. All right, so part C, what lab equipment Well, we've got a constant voltage source, so this is DC power supply would be good. And we're looking at something that, right, so the input voltage is going to step. So we also want an oscilloscope. And we're looking at part D, how do we ensure that data is collected around the time that V in transitions? So if we got time and we've got V in at some point, call it T naught, this input voltage goes from 0 to 1, and we want to start collecting data right around here, right? So we call this a rising edge trigger. And we want this probably around 0.5 volt. Right, so this should happen almost instantaneously, but it's definitely going to pass through 0.5 volt. So if we put a trigger there, then we should start collecting data pretty close to when that switch has occurred. Right, so on the input voltage, right, so we use the oscilloscope, we put that input voltage on one of the channels, and we want to trigger on that channel. So if we were to sketch the setup, I guess, so we have the DC power supply, we have our resistor, and we have our scope. And on one of the channels, we're going to look at the input voltage. And on the other channel, we're going to look at this output voltage. And that should be good for this second question on version 1. So if we take a look at version 2 real quick, C and D are pretty similar. Let's just go through A. We're looking at an equation that describes this unknown node voltage V out. So we have V out is this top right. It's the only unknown again. V in here. Got some current going through that resistor. We've got some current going through that inductor. Right, so this is a little bit more difficult. We can't just jump straight to figuring out what the current is because we have these energy storage elements. Now we have the inductor. So IR, right, minus IL equal to 0. That's our unknown node voltage V out. So we're going to do a little KCL there. So IR, we're starting at V in, we're going to V out. We're going through R, so V in minus V out divided by R. And IL, so what is the current through an inductor? Well, from the physical equations, right, we have this V is L di dt. So V is L di by dt. So if we move over that dt, V dt, and we move over the L, 1 by L is equal to di. And then if we take the integral, we have I is, L is not something that changes over time. We have 1 divided by L times this integral of V dt. Right, so what is the voltage across that inductor? Well, we're going from V out to 0. So that voltage V there in that case, we're left with 1 by L integral of V out dt is equal to I. Well, that is what the current through the inductor is. So this whole expression should be equal to 0. And if we take the time derivative of everything to blast away that integral, we have dV in by dt minus dV out by dt minus 1 by L V out equal to 0. And these guys are multiplied by 1 by R. So the input voltage is not something that's time varying, it's a constant signal. Anywhere the derivative is going to be 0. So what we have is, if I move everything over to the right side, I have 0 is equal to 1 by R dV out by dt plus 1 by L V out. And then if I multiply through by L, I have L by R dV out by dt plus V out. And so here's our expression for V out, and we can see that V out, right, is approaching 0, and we have this kind of like velocity term that's proportional to L by R, right? So we are, for part B, that pretty much answers it. So V out approaches 0 at a rate proportional to L by R. And if we draw this, we have time, we've got V out, and right when this thing is switched, we'll just call that time 0. We start at whatever our initial voltage is, let's call that V naught, and then approaching 0. So that is for part B, and again for part C, it's just a DC power supply and a function and an oscilloscope, and we would look at the response in those two channels and then trigger once that input voltage rises up to 1 volt. All right, so that's good. Moving on to version 3, number 2. So we're looking at this circuit now. So now we have a capacitor, and we want to come up with an equation to describe V out here. We got IC going in, IR going out. We have IC minus IR is 0, and by our device physics, the current through that capacitor given by C dVc. So what is the voltage across that capacitor? It's V in minus V out minus IR. So the voltage across R is V out, right, minus 0, I guess, divided by R. It'll be 0. So again, this voltage of the input, if we take the time derivative there, goes to 0. So we're left with C minus C V out dV out by dt minus V out by R is 0. If I move everything over, 0 is equal to C dV out by dt plus V out by R. And then I just multiply through by R to get 0 is RC dV out by dt plus V out. And again, we can see that V out approaches 0, this time at a rate proportional to RC, right? And that's just telling by this equation that we figured out, V out is going to equal 0 at some point, and it's changing, right? It's got velocity, RC. And for C and D, these are, again, very similar. We need a power supply, oscilloscope, rising edge trigger. All right, good. Moving on to number 3. So for number 3, right, we made the transition from a constant voltage source to a sinusoidal source. And so just taking a look at part A, trying to figure out an equation to describe the unknown net voltage. And I'll do it the long way first. So we have some current going. So this is our unknown node voltage here. So V out since we're in sinusoidal steady state, right, we're assuming that it's sinusoidal, we can find V out using the impedance model. So it's going to be I times the impedance of that capacitor. And since V out, V in is specified in RMS, this current is also an RMS, and we actually need the magnitude of the impedance there. So what is I? So the current I, we're applying V in across this network of R, right? So is the impedance of R plus the impedance of that capacitor. So we got V in divided by R squared plus minus 1 by omega c squared square root, which gives us an output voltage of V in times this ratio, 1 by omega c squared by R squared plus minus 1 by omega c squared square root. Sorry, this is not squared, right? This would be the square root of this, which is just 1 by omega c. So there's our output voltage. For part B, we're looking for what happens to V out considering omega. So let's just look at the simple case. So when omega is 0, right, we've got no frequency, it's just a DC signal. Well, V out is going to charge up to V in. So that is going to be the maximum, that V out can take. So V out is proportional, or rather inversely proportional to omega. So when omega is 0, that's our point of maximum transfer. So V out takes in whatever V in is, so that capacitor charges up completely on the output. And then over time, it's going to allow less and less through. So then for part C, looking at what lab equipment again, that's going to be a function generator instead of a DC power supply, since we're looking at a sinusoidal source there. And we need an oscilloscope. So if we were to sketch the setup, here's my function generator. On channel 1, I'm going to plug these guys here and here, and then here's my scope. So on channel 1, I'm going to look at the input, and on channel 2, I'll look at the output across that cap. And for part D, we're looking at what equipment settings, look at 2 periods of data, right? And that's going to be the time scale or horizontal scale. I accepted either of these on the oscilloscope. All right, so that's number 3 for version 1. Moving on to version 2. It's kind of like the same idea, we just have the capacitor first now. So I'm actually going to skip ahead and kind of use the voltage divider principle. So V out, it's a ratio of V in. And what ratio? So we're looking at R divided by that equivalent impedance. So there's our output voltage this time. And now we're actually proportional to omega, right? So V out increases proportionally to omega. And so when omega is 0, this capacitor takes up all of the charge. And so the output voltage is going to be driven to 0. Right, so if we draw this, we have our output voltage, we start off at 0. And as omega increases, we're also increasing to that input voltage. And for part C and D, these are the same across the other two versions rather. So I'll just skip those and then we'll move on to version 3, question 3. So we're looking at an equation to describe V out again. So V out, and we have we're looking at sinusoidal things again. So I'll just use the voltage divider principle. V out is a fraction of V in, and it's going to be R. Looking at across R, and it's going to be divided by this quantity, R squared plus omega L squared, square root. And we have part B. So what happens when V out? What happens to V out considering omega again? So just looking at the circuit, when omega is 0, that inductor is going to kind of become a short. So it's going to take in whatever value V in has. So V out is inversely proportional to omega, because we have that maximum transfer at omega equals 0. So if we were to draw that, omega V out at omega equals 0, we're at this input voltage and we taper off at higher frequencies. And then again, part C and D are the same, so we don't need to go over that. So go into version 1, question 4. Question 4 is the same across all 3 versions, so I'll just go over this one time. So we're looking for the Thevenin equivalent circuit seen by capacitor C. If I were to just draw that, so C is our load. So I wanted to find the open circuit voltage, right? So that's this guy. Now we have L, R, V in. Well, there's no path for current to flow. So V open circuit is V in, which is the Thevenin voltage. All right. And then we want to find the Thevenin impedance. So we look at I short circuit. Here's our I short circuit. Here's L, here's R, and V in. So I short circuit, we're applying V in across this network of R and omega L, or sorry, the inductor, which has an impedance of omega L. So if we found that, I'll write this out better. So Vn divided by the magnitude of ZR plus ZL, right? And that's going to give us our I short circuit, and then our Thevenin voltage is V open circuit divided by I short circuit, which is V in divided by V in, the quantity V in divided by R squared plus omega L quantity squared, square root, which gave us a Thevenin impedance of R squared plus omega L squared, square root. And this is actually the magnitude of our Thevenin impedance there. So I'll just box this guy up, and we're using magnitudes because the input voltage is specified in RMS, right? So if we have RMS, that's kind of like a measure of the average, the root mean square, right? And when we have root mean square, we kind of lose track of that frequency. And so we need to use the magnitude of the impedance instead of, the complex components. We don't lose track of frequency, sorry, we lose track of the complex algebra. All right, so for part B, we're looking at V out. Supposing that V out is across C, if I were to just draw that, we're saying that this is V out, this is CLR, V in, and if we just use our voltage divider principle again, V out is a fraction of V in, and we're looking at across this guy, but we're applying V in across this entire network, right? So this whole impedance is R squared plus omega L minus 1 by omega C squared, square root. And so that gives us our V out in terms of V in, importantly. So if we just divide over V in, we're left with 1 by omega C R squared plus omega L minus 1 by omega C squared, square root. That gives us our transfer function there. And then for part C, what lab equipment would we use? So we're going to use a function generator because we got a sinusoidal source and oscilloscope. And if we wanted to some people are just drawing it up here. So this is a function generator, right? And we would apply it there. And we got our scope. And we're just looking at the voltage across that capacitor, really. And for part D, we're looking at the transient response instead of the, this sinusoidal steady state. So we would want to swap the function generator with a DC power supply. Unless you got that, so that's good. And like I said, this is the same across version 2. We'll just check all these off. And same as version 3 as well. These are all good. All right, moving on to part 5. So this is the design question. Now for this first one, I had a bit of a typo here. So this is actually a voltage divider, not a tuner. That was from the practice one, right? So we got our voltage divider. And we're outputting something that's a fraction of the input voltage. So that's definitely going to be magnitude. We don't really care about the phase. It doesn't have to, it's not dealing with any kind of time or anything. Part B, is there a point of maximum transfer? No, not really. So as the input voltage goes up, this output voltage is also going to go up. It's still always going to be a fraction of that input voltage. So there's our desired transfer. What lab equipment? So probably a DC power supply. Not really dealing with anything that's frequency dependent, and a multimeter would be fine, or an oscilloscope, I guess. I'm not going to describe an experiment, but you would pretty much just increase V in and make sure that V out's also increasing. All right, so version 2, looks like you guys got this stabilizer device. So in this case, we are looking at frequencies, and it's going to be a constant amplitude, right? So this is most certainly magnitude. Doesn't matter at what time it's being output, it's just we want it to be a constant amplitude. Is there a point of maximum transfer? In this case, no, again, because for all frequencies, we want this output voltage to be constant. And in this case, we want a function generator and an oscilloscope or a meter. So we're just measuring that output voltage and trying to make sure that it stays the same. We're not really looking at something time varying. And for the last version, we are looking at a delay device that outputs a signal at the same signal at a later time. And so we don't really care about the magnitude. It should be the same, but that is somewhat important. You could argue that magnitude is important, but phase is definitely the most important thing here. Because we want something that is outputting at a later time. And so we want some time delay. And if we were to sketch this, we have one signal, let's draw it like that. And we want this other signal to come at a later time. And so here's as time increases, right? So delta t there. There's time, we've got V in as a solid line, V out as a dotted line there. For part C, what lab equipment? So could use a DC power supply or a function generator really. And definitely a scope. You can't really use a multimeter and look at the time delay there. And I'm not going to describe an experiment that was pretty much okay all around. So there's the final exam. Hopefully makes sense after going through that. If you have any questions, feel free to reach out. But overall, good work. I think the average was 75%, not bad. But thanks for tuning in. It was a pleasure working with everyone. And maybe I'll see you again in the future. Thanks for tuning in. See you later.